Okay. Welcome everybody to our next N3AS seminar of the spring semester. And today we're very pleased to have Hajime Sotani from RIKEN to tell us about neutron star constraints from magnetars. So please go ahead.
Yeah, thank you for giving me opportunity to talk here. So today I will talk about a recent our study, neutron star mass and radius constraint from the magnetar QPOs. And this is collaborated with Kostas in Tübingen and Nick in Thessaloniki. And yeah, recently I submit to the archive. And if you want to know the detail, you can see this archive paper. So I want to start my talk. Okay, so maybe you know this is some of constraint from the astronomical observation and also the terrestrial experiment. Yeah, here I assume some specific parameter or fiduciary value of slope parameter L and incompressibility K0. But anyway, if you plot these constraints on the mass and radius plane of neutron star, you can see some current situations. And yeah, to construct a neutron star model, you have to also assume the equation of state that is poorly understood. And yeah, if you assume some specific equation of state, you can calculate the mass and radius like this. So if you get the constraint on mass and radius of neutron star more severe, then you can constrain the equation of state itself. And in this work, we get additional constraint on neutron star mass and radius, and that is this region. So I will talk about how to derive this constraint from the observation by identifying the observed QPO frequencies. So yeah, maybe you know, sorry. Maybe you know the magnetar QPOs have been found, and yeah, up to now several objects from the several objects you get several quasi-periodic oscillations, and yeah, the source of this object is considered as the soft gamma repeater, and the central object of central object of soft gamma repeater is a neutron star. So probably these observed QPO frequency is strongly associated with the neutron star oscillations. So here we assume that these frequencies come from the neutron star oscillations, and by identifying the observed QPO with some specific neutron star oscillation mode, then we try to get some constraint on the neutron star. And yeah, actually, the typical neutron star frequency is kilohertz. This is corresponding to the free fall time. So to identify the kilohertz QPO is more easy, but the lower QPO is more difficult to identify, theoretically identified. And probably the possible candidate is, I think, maybe this is a candidate to explain, to identify the lower QPO frequencies. And one is cluster torsional oscillations. This is this oscillation come from the cluster elasticity. And also the other possibility is magnetic oscillations. Actually, magnetar has a strong magnetic field. So due to the magnetic tension, you can get some specific oscillation magnetic oscillations. And of course, a kind of couple or combination of both of two are also possible. But here we focus on the cluster torsion oscillations. This is because magnetic oscillations strongly depend on the magnetic field strength distribution inside the neutron star, and also the magnetic field, geometry of magnetic field. But such a geometry or strength distribution are quite uncertain. So here we want to remove such uncertainty. But anyway, at the end of this talk, I also mention about the magnetic effect of magnetic field on the effect of magnetic field. And if we assume that magnetic field strength is, let's say, 10 to 15 Gauss, surface magnetic field strength is 10 to 15 Gauss, that time I think the result is not so changed. So anyway, in this talk, we focus on the cluster torsion oscillations. Okay, and this is a rough sketch of neutron star structure. If left in the this direction, neutron star corresponding to the neutron center, and this is this direction is the neutron star surface, and lower density region nuclei form the kind of lattice structure, and that corresponding to the crust. And actually, this is not our new result, but our previous study. There are up to now these QPO are observed, and by identifying this, we identify these QPO frequency with cluster torsion oscillations, then we get a kind constraint on the parameter of L. This is I show briefly how to get this result. Actually, the cluster torsion oscillation can be calculated, theoretically calculated, and that is corresponding to the this solid line or this shaded region. So if L parameter and this frequency strongly depend on the L, because if you change the L, the charge number of nuclei is also change. For example, if you consider the large value of L, the charge number of nuclei is usually decreasing. And to calculate or the shear modulus that is characterize the cluster torsion oscillation, usually proportional to the square of charge number. So if you choose the some smaller value of L, shear modulus is also small. So frequency is decreasing. That is a tendency. But anyway, you can calculate the frequency of torsion oscillations. Then you plot like this, depending on the stellar models. If you see that for example, if choose the L is around 70, that time you can identify all of this horizontal line corresponding to the observation, 18, 26, 29, something like that. This is the observation. And these red or blue or shaded region corresponding to the theoretical torsion oscillation frequency. So if L is around 70, that time observed QPO, all observed QPO can be identified. So if you change the stellar mass and radius, then expected frequency is also become larger or smaller, depending on the mass and radius. That time a suitable value of L is also a shift to left and right. So if you assume typical neutron star mass and radius, for example, 10 to 14 kilometer or 1.4 to 1.3 or 1.3 something to 1.8 solar mass, that time you can get the constraint of L like this. And if you assume the fiduciary value of K0, this range, so in this talk, we focus on the this fiduciary value of K0, and also this fiduciary value of L. And together with we also discuss using this constraint from the QPO observation. Okay, so now what I want to show what we did. Actually, QPOs are newly found. And 2020. And this time the observed QPO is very high compared to the previous magnetar QPOs. But this QPO come from the a magnetar giant flare. And simultaneously, 4 QPO frequency are observed. So here we want identify this observed QPO frequency with the same framework adapted to previous our calculation. So cluster torsion oscillations. And actually this is too high. So we can identify not by using the fundamental oscillation, but overturn of cluster torsion oscillations. Okay. So here we adapt the phenomenological equation of state that is characterized by the K0 and L. And to construct an equilibrium model of a cluster region, we have to choose K0 and L. And also here we calculate or we construct the cluster region by integrating the TOB equation from the stellar surface up to the base of crust. So here, we have to also select the stellar mass and radius. So totally, 4 parameters are needed to construct the one equilibrium model of crust. Yes, and if you choose some value of K0 or different value L, that time the calculated first overturn frequency is to become like this. So each point corresponding to the different equation of state characterized with different value of K0 and L. And frequency itself depends on K0 and L. However, if you plot the frequency as a function of K0 and L, combination of K0 and L like this, that time you can see that frequency is almost well expressed with as a function of this sigma. So hereafter, we are discussing about discussing of the dependence of frequency as of this sigma. Yes, and this is a result with 1.6 solar mass and 12 kilometer. But if you change the stellar radius and mass, that time the frequency is also changed. And and of course, if you change the value of L is the index in YLM, the frequency itself is a little bit changed. But different from the fundamental oscillation, the overturn, the dependence of this value of L is very small. So this is already known. So hereafter we focus on only L equal to mode, and we change, we see some dependence of a ratio of superfluidity, but that dependence is not so strong. So here I omit that dependence. Anyway, if you choose the stellar mass and radius, and you can calculate the torsional overturn of torsional oscillations, and that can be expressed as a function of sigma. And here we show the lowest observed QPO frequency, 835. So in this talk we focus on these 4 high QPO frequencies, and this is a lowest frequency. So you can see that if you identify this frequency with the first overturn, that time a suitable value of sigma is determined depending on the stellar models. Okay, so for example, 1.6 solar mass and 12 kilometer neutron star model, that time probably to identify the observed this lowest frequency, observed lowest frequency can be identified with this first overturn frequency. That time sigma is around 120, like this. So but up to now we got not only one QPO, but also the 4 QPOs, 800 and 800, 104 1400, 2100, and 4200. So now we want construct the or we want explain the all for QPO frequency can be identified with some specific stellar model or some specific torsion oscillations. And this is not trivial, but as shown this figure, we find that it is possible. Actually, this is this red shaded region corresponding to the observed QPO frequencies. And if you calculate the several overtune frequency, actually first, second, third, fourth, fifth, something like that. But here I show only first, second, fourth, tenth of overtune. But anyway, if you see this figure, observed QPO frequency can be identified these fourth combinations. And if the stellar mass and radius is around this, that time, sigma is 120, then observed QPO can be identified with the overtone of cluster torsion oscillations. Okay, so now I try to determine the value of sigma with different neutron star mass and radius. 1.6 solar mass, 12 kilometer is 121. And I change the stellar mass and radius. This figure is 1.6 and 12 kilometer. That is 12 kilometer and 1.6 solar mass. So this point, that is 120 something. If you change the stellar radius and mass, that time again the theoretical frequency change to go up or go down. So corresponding to the suitable value of sigma is shift to left and right, and that value, suitable value of sigma depending on the neutron star model are plotted like this. So if the stellar radius is 10 kilometer like this or 12 kilometer like this, okay. And in the first or second, in the beginning, at the beginning, I said that the fiduciary value of L is 60 plus minus 20 MeV, and K0 is this value. So sigma is a K0 and a combination of K0 and L. So if you know the value of K0 and L, you know the sigma. Now you assume the fiduciary value of L and K0. That time a corresponding value of sigma is this value. Okay. This constraint is corresponding to this shaded region. So if believe this fiduciary value, for example, outside of this shaded region, for example, this region, the stellar model, these points are ruled out from the this fiduciary value. So, for example, if you focus on the 10 kilometer neutron star model, that time mass should be 0.9 something up to 1.1 something. If you focus on the 12 kilometer neutron star model, that time mass is 1.2 around 2 or up to 1.4 or something like that. So using these two constraints, one is to explain the observed QPO, the value of sigma with which the observed QPO can be identified. And also sigma should be in the constraint come from something. For example, come from the fiduciary value. Then you can get the some constraint on neutron star mass and radius. And also here we show the more severe constraint on sigma. That is the K0 is the same, but L is a constraint from the previous QPO frequency I said here. With this constraint L and physical value K, then corresponding value of sigma is this region. That is this dashed line. Anyway, you can get a neutron star mass and radius, this constraint of sigma or this constraint sigma. The resultant mass and radius constraint become like this. So inside this shaded region corresponding to the inside this shaded region. Inside this dashed line corresponding to the inside the dashed line. So this constraint obtained from the as mentioned before, two constraints. One is one observed QPO frequency can be identified with the cluster torsion oscillations, and also the sigma should be a constraint from the terrestrial experiment, something like that. And additionally, we want a constraint or this region make much narrower. So to do to such a purpose, we assume or we adopt additional approach. So actually, sorry, this slide is a little bit messy, but if you consider the low mass neutron star, low mass neutron star means the central density is relatively small. Here we show the several equations of state, the neutron star mass and radius constructed with several equations of state, and we plot up to twice the saturation density. And actually, this mass and radius usually depend on the K0 and L, of course, as you know. But if you plot or if you see the dependence of eta is a different combination of K0 and L like this, that time this lower neutron star model can be expressed with with this eta. Yeah, actually, if you plot the mass constructed with the fixed central density, that time you can plot like this. So yeah, let's say if you choose some equation of state, and if you choose some central density, then you know the value of mass. For example, if you focus on this equation of state and the central density is 1.5 saturation density, that time you can calculate the mass and radius that corresponding to here, for example. And this equation of state has a own value of eta or K0 and L, so which derived to change to the eta. So in such a way, you can plot, for example, central density is 1.5 saturation density. That time, each equation of state, you can calculate the mass and corresponding to value of eta. So you can plot like this. So from this figure, you can see that mass is almost linear, can be expressed linear function of eta if you fix the central density. So mass is plot like this. And this coefficient depends on the central density. So if you change the central density, you see you examine the dependence of C0 and C1, you can see like this. So this coefficient C0 and C1 can be expressed as a function of central density with quadratic function. So finally, you can get a mass of neutron star as a function of central density and also eta. In this similar way, you can derive the formula of Z, gravitational redshift. Gravitational redshift is expressed as a function of mass and radius. So now I want to say that if you know the value of eta, that time you can plot the you can know the mass and the gravitational redshift. And gravitational redshift is a mass and radius. So finally, you know the mass and radius if you know the value of eta. Okay. Now, we assume we focus on the L is this range, K0 this range, corresponding to a value of sigma is this range. And in this case, to identify the cluster torsional, magnetar QPO, we derive this constraint, shaded region. And using L and K0 value corresponding to this sigma, also derive the corresponding value of eta. That is the maybe this value. Okay, and in this range of eta, you can plot the mass and radius. That is this shaded region. So this shaded region corresponding to the same combination of L and sigma, and you can constrain the mass and radius this region. But unfortunately, this is a lower neutron star, low mass neutron star, so we cannot intersection between two regions. If we get an intersection, that time that intersection is a constraint on neutron star mass. So here we further assumption, make a further assumption that is the neutron star radius is almost constant in this region. So finally, we get the some constraint. For example, L and K is in this region. That time, mass and radius of neutron star for observed QPO magnetar is this region. Or more severe constraint is here. So this is a fiducial, and this is a from QPOs. So that is here. So yeah, anyway, this is our main result. And I'm already 30 minutes talk, so I have more 2 slides. So yeah, actually, to derive this constraint, we identify the lowest QPO frequency as with the first overtune. But lowest frequency can be identified second overtune. That may be possible. So here I discuss about that possibility. But actually that is not so good, because if you identify the lowest frequency with the second overtune, that time actually you can identify with different combination of overtune. But in that time, suitable value of sigma is a little bit larger than the previous one. Previous one is 120 something. That here 1.42, and actually this is almost outside of the this shaded region constraint from the terrestrial experiment. So probably this identification is not so good. Actually, we cannot rule out, but usually that is expects the outside of typical neutron star mass and radius. And also, I want to say about the magnetic effect. Actually, this object is considered as a magnetar. So we have to consider take into account the magnetic effect. However, the frequency calculated with including magnetic field. That time, the frequency is increasing if magnetic field is increasing. However, the deviation is not so large if magnetic field strength is weak. And let's say, B mu is 4 times 10 to 15 Gauss, but 10 to 15 Gauss, if the surface magnetic field is 10 to 15 Gauss, the frequency is almost unchanged. Actually, this is a fitting formula how frequencies change due to the magnetic field. And the coefficient alpha depend on the equation of state. And even if assume the 10 to 15 Gauss, the frequency itself change less than 10%. And observed error observed QPO has also some kind of error, and that is more than 10%. So I think the magnetic field effect is not so important if you assume that field strength is less than 10 to 15 Gauss. So here we neglect the such effect. Okay, so sorry, I have over the 30 minutes, but yeah, this is the conclusion. Magnetar QPOs are newly found in giant flare, gamma ray flares, and we identified the observed QPO frequency with the overtone of cluster torsion oscillations. Then we derived some additional constraint of neutron star mass and radius in the this figure. So yeah, that's all. Thank you very much.
Thank you, Hajime, for a very nice talk. Do we have any questions? Please raise your hand on the Zoom, or I see a virtual hand from Susan. So why don't we?
That was a real hand, but.
Yeah.
May I ask my question?
Please.
So that was very interesting. I have a question in regards to your value of L. You deduce from torsional oscillations with respect to the fiducial value.
Yes.
The two data sets are consistent, but you see that your value of L is somewhat larger. I mean, the error bar is more precise, but on average, it's a little shifted up with respect to the fiducial value. So I have two questions. One question is, on what basis is the fiducial value determined? And my second question concerns the possibility of a combination of torsional oscillation and magnetic oscillation. Would there be some value of the magnetic field that would allow you to conclude that maybe L can change if you make the magnetic field just a little bit different from what one has been usually suspected? So I guess I'm just wondering how the magnetic fields might confuse your ability to deduce L.
Okay. So yeah, thank you for your nice question. Yeah, actually, a first question about the fiducial value of L. Yeah, actually, this selection is not so serious. So, for example, some literature, for example, a paper by Wan Lee, they plot the several constraints on L obtained from the experiment or astronomical observation. Yeah, actually, the constraint from the astronomical observation strongly depend on the model. But yeah, anyway, up to now, many constraints on L have been obtained. And you plot these constraints. And yeah, just how to say, if you assume this range, most of the value of L is inside this range. So I think there is no how to say systematic way how to determine this fiducial value. So, for example, the recent constraint on L from the PLX, that is a very large value. So, yeah, I think the way to determine the fiducial value of L is just almost, how to say, by eye or not serious. Can you understand?
I guess you're suggesting that the fiducial value is not extremely well determined.
Yes.
And that therefore it's not surprising that you might see some shift from using the torsional oscillations.
Yeah.
And then the question is in regards to torsional oscillations, whether the magnetic field effect could
Yes, yes.
play a role simultaneously and then shift what we think L might be.
Yes, yes. And maybe that related to this slide. And
Exactly.
yeah.
What
Actually,
makes-
if this frequency is calculated in the neutron star model with magnetic field. And field strength is very small. That is, frequency itself is almost same as the without magnetic field. And in this formula, the denominator, this F with superscript 0, this corresponding to the frequency without magnetic field. And this is a frequency with magnetic field, so this value. So frequency determined with magnetic field effect is normalized with the frequency without magnetic field effect. Then this ratio is almost fitting well with this functional form. And actually the deviation from the maybe small deviation come from around here, and that is corresponding maybe 10 to 15 Gauss. So if you assume that the field strength is less than 15 Gauss, that time cluster torsional oscillation is almost purely oscillating, almost without coupling with the magnetic field. But around 15 Gauss up to, let's say, 4 times 15 or 10 to 16 Gauss, that time you can see strongly coupled with the elastic oscillation and the magnetic field oscillation. And that time, become this region. And finally, if you consider a very strong magnetic field, more than 10 to, let's say 10 to 16 or something like that, that time you can see, in this case, you can see only magnetic field oscillation, magnetic oscillation. So actually, this region, our approach cannot be adapted. But let's say in this weak magnetic field region, that time our constraint is not so changed. But if we can if we will take into account the magnetic field effect, that time okay. So anyway, the frequency is a little bit increasing due to the magnetic field. So for example, this frequency is a little bit larger than the without magnetic field line. So suitable value sigma should be a little bit large, right? So that corresponding to, okay, so this line calculate without magnetic field. If you consider the magnetic field effect, torsional frequency of torsional oscillation is increasing a little bit, maybe less than 10%. So suitable value sigma is increasing, not sure, but maybe less than 10%. So that is corresponding to this plot is a little bit increasing. Each model, the suitable value sigma is increasing. So this model is a little bit increasing. This model also suitable value sigma is a little bit increasing. So that means this line is shift a little bit right. That corresponding to the how to say this line is become around here. So corresponding to mass is a little bit larger if you assume the same radius. So in this case, this is without magnetic field, but if you assume the magnetic field let's say 10 to 15 Gauss, maybe frequency is increasing up to 10%. That time, I think this shaded region little bit shift up.
Oh,
Sorry, my little bit complicated explain, but I hope, yeah, you see the such a magnetic effect in the constraint.
so thank you. You're suggesting that if you included a larger magnetic field effects, your final extracted value of M versus R would be more different from the Fujitsu estimate. So
Right.
thank you very much. That's
Thank you.
clarifying.
Next, I see a hand from Tianqi Zhao. Please go ahead.
Yes, thank you, Sotani, for the very nice talk.
Thank you.
I have a question about the shear modulus you mentioned. You test the density dependence and also equation of state dependence as well?
Yes. Yes. Sorry, I did not prepare the exact formula of shear modulus. But yes, right, you're right. Actually, shear modulus, sorry,
So actually, my question is just how much uncertainty are there in the shear modulus, or is it very well determined?
Okay, actually, if you consider the realistic situation, for example, let's say first we focus on the spherical nuclei. Cylindrical or slab-like nuclei is different, more uncertain. But spherical nuclei is a very large range in the crust region. So let's consider that. Let's focus on the spherical nuclei, and even okay. In the case of spherical nuclei, simple case, the shear modulus is derived as a function of ion number density, charge nuclei, charge of nuclei, and also radius of Wiener cell, or spacing of ion.
So it seems you're assuming like a solid lattice, right?
Solid. Yes, right. Inside the lattice, there are liquid dripped neutron, but yes.
Okay. I also have a question here in this figure, because you show this this L of a different order this angular quantum number. So why is the other L's not detected? I mean, are there any reasons for only those particular ones that show up in your observation?
That is a good question. I think, that is just depend on the initial condition. So, actually, this dashed line, 18, 26, 29, 92.5, 150. This is observed is original this giant flares. And after that, different burst, additional frequency is found. So I think the initial condition when this flare happened, that time the initial condition is very specific, and some of specific frequencies more emphasized.
Okay.
So if you observe the frequency from the same object several times, I think a missing frequency is also observed. And
okay.
yeah, for example, this 57 hertz additional hertz frequency is yeah corresponding to the different variable.
Okay, okay, got that. So it's like there's a piano there, which key they play depends on the initial condition, right?
Yeah, that is very uncertain. Maybe how to yeah, that is very difficult question.
Okay.
Yeah, sorry. Maybe how to cross is breaking or how to magnetic field disconnect, something like yeah, something such a more realistic physical process yeah associated with the initial condition.
And also I have a tiny question about the overturn you talk about. Is it the radal quantum number?
Sorry, overturn?
Is it just the higher radal node number?
Yeah, overturn is yes, yeah. You mean the yes, this.
So that's a higher order radal number, right?
Yes. Overturn is yeah this 1, 2, 4, 10 corresponding to the yeah radial nodal number, right?
Okay.
So first overturn is if you plot the eigenfunction of cluster torsionation inside the cluster region, 1 node. This is a 2 nodes. Yes, right.
So can this thing also be explained by the F mode, P mode as you said?
No. For example, a few kilohertz. For example, 2000 hertz, maybe around this frequency corresponding to the F mode. So I think one or two, yeah, some of them can be identified with the how to say acoustic oscillation.
Okay.
But yeah, here we want to show the possibility to identify with one framework.
Okay.
Yeah, thank you.
Okay, got that. And one last question about the
Yes.
sigma you talk about. This sigma depends on the detailed equation state parameterization you took, right? Because this cannot completely determine your equation state. So there has to be some parameterization of the equation state. Which kind of thing, equation state parameterization are you using?
Okay. Yeah, here I adopt the more phenomenological equation of state that is derived by Oyamatsu Ida. They derived the equation of state as a function of K0 and L. So that is how to say more analytic equation of state, and but their equation of state can be reproduced terrestrial experimental data, and I think that equation of state adapt at least in the lower density region.
Okay. Yeah, thank you for your answer.
Thank you.
Next, we have a question from Sanjay. Please go ahead.
Hi, I'm sorry I joined the talk a little bit late, so I might have missed the early part of it. My question relates to the shear mode velocity profile in the crust.
Yes.
So if you're looking at a n equals 1 or n equals 2 radial overtone, you have to have a map of the shear mode velocity as a function of radius, right? In the crust.
Yes.
Because these different frequencies will sample the crust in different ways.
Yes.
So how much uncertainty is there because of effects like entrainment, which changes the shear mode velocity? So you had the shear modulus, which somebody asked about earlier, but in addition to the shear modulus, you need to know what is the effective mass of a nucleus as it moves in this crystal.
Okay. Yeah. Okay, so yeah. Okay, so here we adopt very simple simple or standard shear modulus derived by Strohmeyer 1991. So that is very simple. For example, the nuclei is assumed point-like, something like that. So yeah, if you assume additional effect in the shear modulus, I think shear modulus itself change around 10%. So shear speed is root shear modulus over density. So yeah, frequency itself is not so change, but yeah, you can see a few percent dependence in the such uncertainty in shear modulus, I think.
Yeah, I don't know. The shear modulus may not change very much, but
Yes.
shear velocity is shear modulus divided by the
Density
mass density of the ions. It's not the total density. It's the mass density of the ions. And the mass density of the ions can be uncertain if there is entrainment. So I think the shear velocity in the inner crust can change by 50%.
Okay. Yeah, sorry, I understand your question. Yeah, actually, we did not change the mass density of ion, but okay, here we changed the different kind of property. So yeah, actually, in the relativistic framework, shear velocity is proportional to square of shear velocity is proportional to shear modulus derived energy density plus pressure, something like that. And I think but in the density region, in the crust region with very dense, high density, the neutron dripped from the nuclei, and some of them behave as a superfluid. And if such a neutron star exists, superfluid neutron star, probably that mass density cannot be affected on the inertia of this torsion oscillation. So here we assume that the drip, how much ratio of super, how to say, we introduce this ratio. This ratio is the number of neutron behave as superfluidity to the this is a dripped neutron. So if this ratio is 0, that time dripped neutron, all the dripped neutron behave as a normal fluid. And if this value is 1, that time dripped neutron behave, all the dripped neutron behave as a superfluid. And I think this to 1 or 0 is the extreme case to the superfluidity, or I think that corresponding to the mass density of ion. So in this case, even in this case, the frequency, at least the overtune, the frequency is not so changed. This is the case of this ratio is 0, and this is a 1. So for example, the overtune, that density or that mass density is not so significantly important. But yeah, it's right. That is right for considered the fundamental oscillation. Fundamental oscillation, the frequency is dramatically changed if you assume that this ratio is 0 or 1. That is become the answer for your question.
Yeah, I think it partially answers the question.
Yeah.
Thank you.
Yeah, thank you.
I see a question from the N3AS folks.
Yeah, I had a very basic question. Hopefully it won't take that long to answer. Can you just give kind of a physical scaling reason for the power laws in eta and sigma, you know, the 4 to 5 and the 1 to 2 with K naught and L.
Sorry.
If you go to your definition of sigma, right, it's K naught to the 4th, I think, and L to the 5th.
Sigma mean this sigma. Yeah, sorry. Sigma and
Yeah. Is there any particular reason for the choice of the 4 and the 5?
Sorry, no. As mentioned before, if you calculate the frequency by changing the K0 and L, that time frequency is very distributed. But I just change the combination by hand. Then we find this combination is good. So I think you may find more suitable combination. Yeah, so this is one example, and I think this is not unique.
Okay, thank you.
Yeah, thank you.
Are there any more questions? I don't see any additional hands right now. If not, let's thank our speaker again.
Well, thank you, Hajime.
Thank you.
And I will end the recording.